In this session, we'll investigate highway pavement and shoulders. We'll begin our study with pavement surfaces. Through this study, you'll learn 1. The purpose and functional requirements of highway pavement surface and shoulders. 2. The elements of pavements and shoulders, as well as the characteristics that contribute to poor performance. And 3. The proper and improper installation and maintenance procedures. The miles of unpaved roads in the nation are low-level, low-speed, and low-volume roads. Major highways are, of course, paved. We're concerned with high-volume major roadways, so we'll be studying only paved surfaces. There are two categories of pavements, flexible and rigid. Flexible pavements include asphaltic concrete surfaces. Rigid pavements are constructed with Portland cement concrete. For the pavement to serve as a functional surface for moving vehicles, it must provide 1. A durable travel surface that will withstand the repeated wheel loads of vehicles. 2. Adequate drainage, including removing water from the travel surface and from the lower portions of the pavement thickness so that the structural strength of the base is not weakened. And 3. A skid-resistant travel surface that will allow sufficient friction for expected traffic operations. We're concerned primarily with the last point, a skid-resistant surface. Travel surface and adequate drainage are affected by the quality of materials and the construction techniques used. And we won't be discussing pavement design and construction at this time. So, after we look very briefly at strength, we will focus on friction and vehicle steering factors that influence the safety of vehicle operations. For maintenance cost efficiency, the major criterion for a pavement is that it be able to carry traffic without breaking up, cracking, heaving, or otherwise deteriorating. The selection of materials in the surface course and in the soil beneath it greatly affects the durability of a pavement. Only approved pavement designs should be used for highway construction. The National Highway Institute sponsors another course on pavement design, so we'll leave that subject now and continue our study of skid resistance. One of the primary safety functions of a pavement is to provide skid resistance. Skidding takes place in a very complex environment. The abilities of the driver, the condition of the vehicle and its tires, and the characteristics of the pavement all interact to provide resistance to skidding. 3 factors increase the possibility of skidding: water on the pavement, high vehicle speeds, and finally, polished aggregate. Polished aggregate is the single most important pavement contributor to slipperiness. These are also factors which lower pavement skid resistance. To understand skid resistance, we must first understand friction and how it is measured. Friction is resistance between the pavement and the tires of vehicles. Resistance allows drivers to stop, accelerate, and turn without losing steering control. Friction is affected by pavement drainage, vehicle speed, pavement texture, and aggregate selection. Pavement friction is measured by a locked wheel skid trailer. The standard test speed is 40 miles per hour and is reported as SN40, or skid number at 40 miles per hour. Uniform specifications should be followed when measuring friction. The amount of relative friction is expressed as a skid number. The skid number is the coefficient of friction times 100. The higher the number between 0 and 100, the higher the friction. Skid numbers refer to wet pavement conditions. I mentioned before that polished aggregate is the single most important pavement contributor to road slipperiness. The influence of a polishing aggregate needs our special attention. As traffic wears down the aggregate particles, the surface becomes smooth and friction decreases. When a highway is first opened, it may register an acceptable skid number because it has not been worn down. As the aggregate is polished by traffic, the surface can degrade rapidly and present serious skidding problems. The most stable surface conditions occur about 24 to 30 months after a road is opened. A polished surface can degrade to a skid number approaching that of ice when vehicles travel over it at the higher speeds. However, a good non-polishing aggregate pavement will maintain acceptable skid numbers over a wide range of speeds. Surface construction materials need to be selected for safety and durability. Then, additional maintenance activities such as adding skid-resistant surface overlays can be reduced. Pavements constructed of non-polishing aggregates actually increase in safety with time. As traffic moves over the surface, new rough surfaces are exposed and friction is increased. So you can see the use of a good wearing surface is essential to provide friction. The texture of the road surface also greatly affects skid resistance. Pavements should have two types of texture: macro texture, the coarseness of the surface, and micro texture, the fine grittiness that provides what we think of as friction. Macro texture protects against hydroplaning. Some portions of the pavement project above the film of water to allow vehicles to maintain some contact with the roadway. Macro texture is most important on roads with traffic speeds of 40 miles per hour or more. Microtexture can be achieved most effectively in an asphalt pavement through a good quality non-polishing aggregate. If such aggregates are too expensive to include in a total mix, they can be provided on the surface by sprinkle mixes or surface treatments. In concrete pavements, microtexture is provided through mix design, quality aggregates, and construction controls. Dense graded mixes can be improved with open graded surface courses or surface treatments or quality aggregate. Concrete pavements can be textured during construction. Macro texture can be provided on old concrete pavements by grooving. Water on the pavement can greatly reduce friction. When friction drops, vehicles traveling above 40 miles per hour can hydroplane on the wet surface. When hydroplaning occurs, friction has dropped to zero. Two important factors affect pavement drainage. First, cross slope, and second, the pavement surface's ability to allow water to move away from under the tires. Without drainage, a film of water lays on the roadway and can cause hydroplaning. When a tire hydroplanes, it rides on the water rather than the road. Steering control is lost because the tire-to-pavement friction is lost. Hydroplaning is a problem on any road where vehicles can travel at speeds above 40 miles per hour. So hydroplaning is not only a rural problem, but also one that can happen on arterial streets. The likelihood of skidding increases with higher speed of travel. So the surfaces of high-speed roadways need to provide friction for the increased speeds. In addition to texture, adequate cross slope is needed to drain water from the pavement surface. Cross slope also affects steering. In road construction, the design values of the cross slope should be followed closely to balance drainage and steering problems. Too great a cross slope creates steering problems. Too little a cross slope doesn't adequately drain the surface. To enhance drainage even more, open-graded asphaltic paving mixtures are used. FHWA specifications for the mix are available. The open-graded mix was developed to produce a surface that would allow surface water to flow down through a porous thickness and then out to the side on a smooth surface. Although the open-graded mix will not substitute for good cross slope, it does aid friction. Water in front of a tire can flow down through the pavement voids and away from the tire. Removing water from under the tire reduces the potential for hydroplaning. This photo shows a truck traveling on a conventional pavement. The tire splash is considerable for a light rainfall, 0.2 inch per hour. Here we see the same truck traveling on an open graded mix test pavement 200 feet downstream. The tire splash is greatly reduced, and the pavement appears almost dry in comparison to the conventional pavement. Moderate rainfall is drained from this roadway by the open graded mixed pavement. Pictured here is the roadway in a 0.2 inch per hour rainfall. The surface appears quite dry. However, with a heavier rainfall, the voids in the pavement aren't adequate to carry away all the water. With a 0.6 inch per hour rainfall, a considerable amount of cross-pavement runoff occurs on the surface. Milling is a successful method of refurbishing highways. The old surfacing material is removed first. In that way, the thickness of the roadway is not increased, and the basic minimum clearances can be maintained. A small amount of new asphalt and mix are relaid on the milled roadway. The cost effectiveness of this operation has made it extremely successful, so that it is being used on many miles of highway. A milled surface can provide acceptable friction even before the new surface is applied. But too rough a surface isn't desirable because the wavy patterns can cause steering problems for small cars and motorcycles. For Portland cement, concrete cement, surface friction may be improved by 1. Tining fresh concrete, 2. Grooving existing pavements, or 3. Applying an overlay surface on top of the old concrete surface. Tining is the best surface texturing method approved for fresh concrete. Brooming alone is no longer accepted. Tining in the transverse direction is generally used on tangent sections. Tining is performed by dragging a steel comb through a plastic mix. The steel tines are flexible enough to deform around the large aggregate without pulling it out of the mix. Portland cement concrete pavements can be grooved to provide space for the water to drain. The grooves also provide a rough vertical edge for tires to grip. The grooves are sawed in existing concrete pavements. To increase stopping friction, grooves should be sawed across the lane. To increase friction on curves, the grooves should be cut in the travel direction. Friction is increased by the action of the tire biting into the vertical edge of the grooves as it tries to slide across them. Other conditions in the paved travel lanes can adversely affect steering and driver performance. Now, here we see 5 surface characteristics that can interfere with the driver's ability to control a vehicle: road drop-off, roughness, pavement joints, uneven lanes, and super elevation. We'll look first at super elevation. Here you see a road with proper super elevation, a condition which greatly affects vehicle stability. When proper super elevation is not provided, as shown in the first curve here, a serious safety hazard can result. Serious steering problems can be caused by a rutted track or drop-off along the pavement. The tire snags on the pavement edge when the driver attempts to steer back onto the paved surface. Oversteering usually results, and the vehicle can cross over into approaching traffic or adjacent lanes. This particular drop-off was caused by applying an open graded mix course. The edge should be more gently feathered, but the shoulder surface should not be overlaid with dense mix that would prevent the water from escaping. Here's an example of deep rutting at the pavement edge caused by a combination of wheel action and erosion. Compare the size of the 35mm camera case in the foreground with the depth of the rut. Raveled pavement edges cause steering problems when a wheel drops off the pavement. Because drivers stay away from raveled edges, the effective lane width is reduced. Structural problems in the roadway will also be created. The second hazardous surface characteristic is rough pavement. Such surfaces cause wheel bounce. Then, friction is greatly reduced because the tire loses contact with the surface. On horizontal curves, the situation becomes even more hazardous because the vehicle is being forced outward due to centrifugal forces while traveling around the curve. The next hazardous surface characteristic we'll look at is uneven lanes. Wheel ruts in the pavement produce uneven lanes and thus steering problems. Wheel ruts greater than 1/8 to 3/16 inches deep should be identified for leveling through grinding and/or an overlay. These wheel path depressions are an indication of potential wet weather skidding problems. An uneven pavement surface can trap water and cause hydroplaning. Roller coaster pavements cannot accommodate drainage and allow water to collect. Drivers don't know that the water hides depressions in the pavement. When entering these water-filled depressions, drivers can unexpectedly lose steering control. Inspection of the roadway during or immediately after a heavy rainstorm will identify sections that drain poorly, so that corrective action can be taken. Here, you see a driver entering a water-filled depression. Hydroplaning can occur even in an urban section like this, since many urban roads are speed zoned above 40 miles per hour. This water can also be splashed onto other adjacent vehicles, causing loss of vision and control. You've seen that the condition of roadway surfaces greatly affects driving safety. The edge of the roadway, the shoulders, are also an important part of the roadway safety system. We'll study shoulders to 1. Define their purpose and function. 2. Identify the characteristics of shoulders that contribute to proper and improper performance. And 3. Identify proper and improper installation and maintenance procedures that affect safety. Shoulders must be installed and maintained properly to fulfill their purpose. Field experience with shoulders indicate that they contribute to highway safety and desirable traffic operations in many ways that drivers appreciate. Shoulders generally are classified in these categories: stabilized, paved, and unstabilized local roads. Stabilized shoulders consist of sod, sand, gravel, or any other materials which can carry at least occasional traffic wheel loads. Paved shoulders include Portland cement concrete or asphaltic concrete. They have a hard applied surface coating and a stable base. Shoulders serve the different purposes shown here. These purposes are based on their type of construction, the traffic laws, and the local driving practices. Any shoulder should provide the capability for emergency stopping. The shoulder should also be a surface where drivers can recover steering control when swerving out of the travel lane to avoid a collision or a hazard. Stabilized shoulders provide the surface needed for emergency stopping and evasive action. When a shoulder is paved, many other functions are possible in addition to these two. Paved shoulders can provide additional travel space for slow-moving or wide vehicles, for vehicles to bypass construction and maintenance equipment, and for additional travel lanes at peak travel hours if properly designed to carry these loads. Paved shoulders also permit greater steering tolerance, protect the pavement edge from deterioration, and increase operating capacity. For stabilized shoulders, the stabilized edge should extend outward at least 4 feet from the pavement edge to provide a stable surface for occasional wheel loads. When the stabilized shoulder is sod, it should be mowed regularly so that drivers recognize that it can be driven on in an emergency. When the stabilized shoulder is gravel, it should be compacted to reduce the possibility of loose gravel flying onto the travel lane and being thrown into windshields. Ruts, depressions, and pavement to shoulder drop-offs should be graded out or backfilled. Paved shoulders, even those only 2 feet wide, will increase the effective lane width by greatly reducing the drop-off and loss of steering control problem. Shoulders from 2 to 6 feet in width increase traffic capacity and offer the pavement structural protection. Shoulders that are 8 feet wide are the minimum width to allow a passenger vehicle to stop on the shoulder and be completely off the travel lane. An 8-foot shoulder also allows space for moving operations. Shoulders of properly designed strength and at least 10 feet wide can be used as turning lanes or bypass lanes. And finally, shoulders of 12 feet width with increased strength design are needed where truck volume is high to provide a turning lane. At least 8 factors influence a shoulder's ability to serve its intended function. Some are structural, others are related to drivers. Shoulders need strength to handle repeated wheel loads and width to permit vehicles to drive on them. Without the proper strength, the shoulder does not function, and maintenance costs increase. The standards of the shoulder's construction will determine its potential use. A weak base or surface construction will not stand up to repeated wheel loads or to erosion. So certain requirements need to be anticipated for the construction of effective shoulders. If shoulders are to be used for traffic movement, newly added shoulders should be constructed to standards similar to those of the travel lane. If future widening is planned, base construction should extend far enough outward to construct the future lanes. The width, as well as the strength of the shoulder, must be part of plans for future road widening. If future plans include potential widening into a 4-lane road, the shoulder width for the time before widening needs to take into account the future 4 lanes. The width should be wide enough to allow 2 full-width lanes in each direction, plus striping and minimum outer shoulders after widening. Shoulders added near intersections for future use as acceleration, deceleration, or turning lanes should be 12 feet wide to permit truck turning and channelization edge striping. I mentioned before that cross slope is an important factor in road safety for effective water drainage. This is a good time to repeat that the cross slope must be balanced. Too steep a slope encourages loss of steering control. Too shallow a slope doesn't allow effective drainage. State and AASHTO standards should be closely followed. Severe increase in cross slope between the travel lane and the shoulder produces a ridge or barn roof profile. Vehicles moving from the travel lane to the shoulder experience a sudden pitch-over motion. In wet weather, skidding can occur when the driver oversteers to correct the travel direction. The cross-slope differential should not exceed 8% in super-elevated cross-sections to minimize the pitch-over effect. Smaller vehicles are even more susceptible to pitch-over. When roads are repaired, resurfaced, or reconstructed, the design of the cross slopes are often changed. While the original cross slope adhered to acceptable pitch-over rate and drainage runoff, the construction work may make the new cross slope unacceptable. Overlays applied to the travel lanes and tapered abruptly to the shoulder will produce a much steeper cross slope differential. Thus, the pitch-over effect is increased. Conversely, surface coats applied to shoulders but not to travel lanes create a raised ridge at the outer edge of the travel lane. Steering a vehicle up over this ridge is more difficult, and drivers are reluctant to move over to the shoulder. If the driver moves over too far, the tire can snag on the ridge. In addition, water can pond on the travel lane, and reverse drainage can occur if shoulders are surface coated enough to completely remove the outer drainage cross slope. The shoulder joint itself presents major maintenance problems that we need to be aware of. Separation of the shoulder and travel lane edge, as you see here, allows water to enter the base of both the travel lane and the shoulder. Excessive water under the pavement reduces the strength of the base material. Eventually, the pavement settles or breaks off. The process of deterioration is then accelerated. Differential settling occurs if the base materials are different, and vegetation will grow and cause further edge raveling. Damage to the shoulder joint can then cause problems to drivers. For example, drivers usually move to the left, away from the separated shoulder joint and deteriorated pavement edge, reducing the space for safe travel. When drivers must move from the travel lane to the shoulder, additional problems exist. If the shoulder is lower than the main lane, a drop-off condition occurs. If it is higher, a step-up condition is created. Both conditions adversely affect safety. The shoulder itself can deteriorate, and shoulder deterioration at the outer edge is a warning that the deterioration will progress toward the travel lane. Water erosion under the pavement and vegetation destroy the base material that supports the surface. Water can't drain away from the shoulder if soil and debris form a dike at the edge. Water then permeates the road base. Grass is another hazard to the shoulder edge. It can encroach on the shoulder surface, encouraging edge raveling and reducing the effective shoulder width. Drivers perceive the shoulder to be narrow, can't see glass and debris in the weeds, and will not pull completely over onto the narrowed shoulders. Whether or not drivers actually drive on the shoulder, a definite contrast between the travel lane and shoulder should be maintained. The contrast can be achieved by color and/or texture differences between the two surfaces. This contrast shows drivers that the shoulder is definitely reserved for special purposes. Also, contrast of the shoulder helps delineate the travel lane in poor conditions such as rain or fog. Another important reason for contrasting the shoulder is that for areas where driving on the shoulder is prohibited, drivers can easily recognize the shoulder by color or the changed sound caused by the different texture. Here, you see a shoulder with no differentiating color or texture. The only shoulder distinguishing feature is the painted edge line. When the edge line is deteriorated, there is no definition of the two surfaces. For this reason, edge lines must be maintained to a high degree of reflectivity and brightness when the shoulder surface is the same color and texture as the travel lane. Look at the difference when shoulders have both a color and texture that is different from the travel lanes. The appearance of the shoulder can enhance or totally nullify the driver's decision to use the shoulder. To ensure that the shoulder is functional, to provide a margin of safety, attention must be given to both construction and maintenance. Routine maintenance can identify and correct the pavement and shoulder problems we've discussed. Poor surface conditions, poor drainage, and hazardous pavement edges can be identified during travel to and from maintenance locations. Then, the areas should be visually identified so that improvements can be scheduled. Often, what seems like a minor repair is in truth an indication of more severe problems. Sections of pavement containing edge raveling, roadside wheel ruts, and separated pavement joints should be identified and programmed into future maintenance projects. If they are left unattended, the repair costs will be much higher. Pavement sections near bridges and other structures need special critical inspection. In many cases, pavements near structures settle when the fill material behind the abutments is not compacted enough. In snowbelt regions, ice forms first on bridges. Steering control is lost when vehicles bounce onto the bridge deck from the roadway. Curves also need careful inspection to identify pavement edge drop-off ruts caused by off-tracking vehicles. In severe cases, pavement widening or shoulder strengthening may be warranted at curves where this happens frequently. Maintenance field personnel can give the most valuable information of areas that will need future improvements. Their comments and suggestions should be sought and communicated to the proper administrative source. Develop that communication channel so improvements can be programmed into future maintenance or reconstruction projects. We'll now watch a film on wet weather accidents. Parts of the film will illustrate our discussion here today. After the film, you'll have the chance to give your comments and viewpoints about today's lesson.
These films were taken on a new circumferential highway around Washington because the roadway was not engineered to be safe in wet weather. This is what happens. This particular stretch of highway has since been redesigned and made safer. Accidents have fallen off dramatically. But we'll be looking here at just a few of the accidents that happened within the course of a 2-day period. The Public Works Committee is concerned with how many other danger spots like this may exist throughout the country. That's the purpose of the hearings we're holding in Washington this week. This should be a safe highway. It's a new highway, but there are several things wrong. The grade is too tight. Here we see the same curve from the opposite direction. This poor fella was so excited that when the car stopped skidding, he drove it into the guardrail. Watch the station wagon. The driver of this station wagon is the mother of 4 children. Luckily, she escaped serious injury. But before the station wagon could be removed, you see another car skids down the same embankment. This road needs an aggregate with skid-resistant qualities. It has since been provided. Watch the Volkswagen. Now keep your eye on this truck. This could have caused a multi-car accident on the lower roadway. Only great good fortune prevented it. The Public Works Committee wants to know how many other spots there are like this in America. Here's another location and another day. He almost gets run into coming around and getting started again. These films were taken by professional investigators of the Public Works Committee of the United States House of Representatives.